Today, we want to talk to you about a paradox that has challenged and continues to challenge the brightest minds in science for decades. Have you ever wondered how something could be both alive and dead at the same time? This seemingly absurd question touches the heart of one of the deepest mysteries in physics, the famous thought experiment of Schrödinger's cat, a symbol of the bewildering nature of quantum mechanics. Imagine standing in front of a closed box. Inside, there is a cat, but you cannot see what's happening inside the box. However, you know that the cat's fate is linked to a subatomic event, like the decay of a radioactive atom. If the atom decays, a lethal substance is released, killing the cat. If the atom does not decay, the cat remains alive. So far, everything seems straightforward. But this is where quantum mechanics comes into play, and the concept becomes incredibly more complex. In 1935, Austrian physicist Erwin Schrödinger conceived this thought experiment to highlight how the laws of quantum mechanics, which govern the microscopic world, could produce paradoxical results when applied to the macroscopic world, what we can directly observe, such as a cat. According to classical physics, the cat should either be alive or dead. There would be no room for an intermediate condition. But according to quantum mechanics, as long as we don't open the box and directly observe the system, the cat exists in a superposition of states. It is both alive and dead at the same time. But how is that possible? The answer lies at the heart of quantum mechanics and one of its most controversial concepts, quantum superposition. This fundamental principle holds that a quantum system, like a radioactive atom, can exist in multiple states simultaneously until it is measured. Only at the moment of measurement, when we observe the system, does the system choose a definite state. It's as if the act of observation itself interrupts the mysterious dance of superimposed states, forcing reality to make a decision. In the case of the cat, until we open the box, it exists in a superposition. It is both alive and dead at the same time. But the paradox resolves itself the moment we open the box. We observe the cat in a well-defined state, either alive or dead. This phenomenon is known as the collapse of the wave function. According to quantum mechanics, the wave function describes the quantum state of a system, containing all possible information about it. As long as we don't measure it, the wave function can exist in a superposition of states. But as soon as we measure it, the wave function collapses, and the system assumes a definite state. This leads us to an even more intriguing question. What exactly causes the collapse of the wave function? Is it really the act of observation that turns uncertainty into reality? Why does the superposition of states exist only until we directly observe the system? These questions touch on one of the most profound and unresolved problems in quantum physics, the measurement problem. In the quantum world, it seems that the observer plays a crucial role in defining reality. But classical physics, and even our common sense, tell us that the world should exist in a well-defined state, regardless of whether or not we observe it. However, quantum mechanics seems to suggest otherwise, challenging our deepest intuitions. Schrödinger designed his paradox to criticize this view and show how absurd it is to apply quantum laws, valid for subatomic particles, to macroscopic objects like a cat. But his thought experiment has sparked a discussion that continues to stimulate modern physicists. Over the years, various interpretations of quantum mechanics have emerged, seeking to explain Schrödinger's cat paradox and the problem of wave function collapse. One of the most famous is the Copenhagen interpretation, proposed by Niels Bohr, which holds that quantum superposition is real only until a measurement is made. Once we measure the system, it assumes a definite state. But there is another equally fascinating interpretation, the many worlds interpretation, proposed by Hugh Everett in the 1950s. According to this theory, every time we make a measurement, the universe splits into multiple parallel universes. In one of these universes, the cat is alive. In another, it is dead. Both realities exist simultaneously, but we can experience only one. But the mystery doesn't end here. There is another crucial concept in quantum mechanics that we must consider: quantum decoherence. According to this theory, quantum effects are not observable in macroscopic systems because such systems constantly interact with the external environment. For example, the cat in the box is never completely isolated from the rest of the universe. This interaction with the environment causes the dispersion of quantum superposition, making it impossible to directly observe the simultaneous state of life and death of the cat. Decoherence explains why we don't observe strange quantum phenomena in the macroscopic world, but it doesn't completely solve the problem of wave function collapse. The mystery remains. With his thought experiment, Schrödinger, along with other physicists, gave us just a glimpse of a universe far more complex and mysterious than we can imagine. Schrödinger's cat paradox is not just a simple mental exercise, but it forces us to reflect on the very nature of reality. Quantum physics shows us a world governed by uncertainty and probability, where our classical intuitions clash with a reality far stranger than we ever imagined. If you're fascinated by these topics and want to dive deeper into the mysteries of quantum physics, I recommend two must-reads: The Order of Time and Reality is Not What It Seems by Carlo Rovelli. These books will take you on a captivating journey through time, space, and the fundamental laws that govern the universe, explaining complex concepts in a clear and engaging way. Finally, to further deepen your understanding, I suggest The Grand Design by Stephen Hawking, where the famous physicist discusses many of the most advanced theories in modern physics, including the nature of reality and the role of the observer in quantum physics. Thank you for joining us on this journey through one of the greatest mysteries of modern physics. If you enjoyed this video, don't forget to leave a like, subscribe to the channel, and ring the bell to stay updated on future content.